Welcome to Math, where problems are no problem. Imagine you're on a jury. The defendant is assumed innocent until the evidence is overwhelming enough to say otherwise. You don't walk in assuming guilt. You walk in assuming innocence and only change your mind if the proof is strong. That courtroom logic is basically what statisticians do every time they run a hypothesis test, and by the end of this video, you'll be able to run one yourself. Let's set up the case. In statistics, a hypothesis is just a claim about the world that we want to check using data. Like, this coin is fair, or this cereal box weighs 500 grams on average. Every hypothesis test actually uses two competing claims. The first is called the null hypothesis. Think of it as the innocent until proven guilty claim, the boring default that says nothing unusual is going on. The second is the alternative hypothesis. The claim you suspect might actually be true, the one that says something is going on. Here's our case for today. A cereal company claims each box contains 500 grams of cereal on average. You're suspicious they're skimping on you. So you buy 25 boxes, weigh them, and find the average weight is 495 grams. Is that just normal randomness? Some boxes are a little over, some a little under, or is it real evidence the company is underfilling boxes? First, we write down our two claims. The null hypothesis, the true average weight really is 500 grams, and our sample just happened to come in a bit lower by chance. The alternative hypothesis, the true average is actually less than 500 grams. They're really underfilling. Now, before we look at any calculation, we need to set a threshold for how much doubt is enough doubt. That threshold is called the significance level. It's basically how strict the jury is willing to be before shouting guilty. The standard choice almost everyone uses is 5%, written as 0.05. That means we're only willing to reject the company's claim if there's less than a 5% chance we'd see results this extreme purely by random luck. Next, we need to measure just how far our sample result is from what the company claims, not in grams, but in a standardized way that lets us compare it to a known scale. This measurement is called a test statistic, and since we know how spread out box weights typically are, let's say past data shows a standard deviation of 15 grams, we can calculate what's specifically called a z-score. A z-score just tells you how many typical spreads away from the claimed average your sample result landed. Here's the formula, spoken out. Take your sample average, 495, subtract the claimed average, 500, giving you -5, then divide by the standard deviation, 15 divided by the square root of your sample size, 25. The square root of 25 is 5. So 15 divided by 5 is 3. -5 divided by 3 gives us a z-score of about -1.67. Now we compare that number to a boundary line called the critical value, the exact cutoff point where suspicious officially becomes reject the null hypothesis. For a 5% significance level, checking only the low side, that boundary sits at -1.645. Our z-score, -1.67, is further out into that shaded tail than the boundary of -1.645. It cleared the bar for suspicion, so we reject the null hypothesis, meaning the evidence suggests the true average box weight is genuinely below 500 grams, not just random noise. Before we celebrate catching the cereal company red-handed, let's sanity check this. If the true average really were 500 grams, getting a sample average this low by pure chance would happen less than 5% of the time. That's precisely what our comparison to the 0.05 significance level just confirmed. It's like a courtroom, where the fingerprint evidence alone wouldn't convict. But combined with everything else, it tips the scale past reasonable doubt. That tiny probability of getting this result by fluke, if the null hypothesis were actually true, is often summarized in a single number statisticians call a p-value, and in our case it's smaller than 0.05, which is exactly why we rejected the claim. So here's the whole process in one breath. State your two competing claims. Pick how strict you're being, measure how far your data strays from the claim using a standardized score, and check if that score crosses into the rejection zone. If it does, the evidence says something real is going on, not just random luck. The key insight to remember: hypothesis testing never proves anything with total certainty. It just asks, how surprising would this data be if nothing unusual were happening? And if the answer is very surprising, we side with the alternative. If this helped, the next video covers p-values in more depth. And if this channel is helping you make sense of statistics, subscribing helps more people find it too.